All right, so in class we started to talk about problem one from a problem set. We ran out of time in solving it, so I want to try and do it here in a screencast, also in hopes that we can speed up class just a little bit to get caught up. So all right, so let's take a look at problem one again and let's work through it. So in problem one, the data below give the dew and bubble temperature of methanol ethanol mixtures at 1 bar, and then we're asked a series of questions related to it. Okay, so the first thing is this is TXY data, and so what I'm going to do is I'm going to first make a sketch of a TXY system for an ideal system, and then we're going to try and think about what this data actually is that we're given, okay, and what it corresponds to. So all right, so I'm going to start with trying to sketch a TXY phase diagram. Again, it doesn't matter how nice your picture is. Mine is going to be even less pretty here on my tablet as compared to on the board, but that's okay. So I'm going to draw a line of pure component 1. This would be pure component 2. Okay, over here, this is going to correspond to T2 sat. Over here is going to be T1 sat. When I plot with respect to the most volatile component, remember pressure is fixed in my TXY. So at constant pressure, the most volatile component is going to have the lower pure component saturation temperature. It's going to boil most easily. And so I'm just going to draw two curves. And there's my sketch of my TXY. All right, so in terms of data that's given, okay, so we're given X1 or Y1 and then T2 and T bubs. All right, well, what does this correspond to, right? So how I can essentially picture this is I'm given data for a vertical, a line of constant composition. Okay. So remember my TXY, this is going to be low temperatures favor liquids. Okay, high temperatures favor vapors. The line separating vapor from two-phase is going to be my dew line. Line separating my liquid from two-phase, that's going to be my bubble line. Okay. Cool. So if I have a mixture of composition, say Z1, and I heat it up to my two-phase region, where I hit my bubble line, we're going to call that our bubble point. So that's going to be T bubs. So it's my bubble point temperature for the mixture. And if I had a vapor and I were to cool it down where I first enter my two-phase region, where I hit my dew line, well, we call that T dew. Okay. So the data that we're given is at a given composition, so say I have a composition of 0.3, X1 or Y1, we're given T dew and T bubs, where T dew is greater than T bubs, right? So what we're given is if this were a composition of 0.3 mole fracs, okay, we're given T dew and T bubs for a mixture of that composition. Okay. The other way I would think of this data, if I were to plot it, I would plot X versus T bubs, and we'll do that at the end, and Y versus T dew to generate my phase diagram. So in the context of A and B, how we'll think about this data though is if I have my TXY, if I draw a line of constant composition, it's going to give me the bubble point and dew point temperature for a mixture of that composition. Okay. Cool. All right, and so there's my bubble line, dew line, two-phase in between, vapor up top, liquid on the bottom. Now we said when we plot with respect to the most volatile component, T2 sats could be greater than T1 sat. So if I look at the data, okay, this is T1 sat down here, T1 sat 64.20 degrees C. Okay, yeah, T1 sat 64.2 degrees C, and T1 sat 78 degrees C. So we get T2 sats greater than T1 sat. We're plotted with respect to the most volatile component. All is good. Cool. All right. So now I'm going to emphasize, right, one of the most valuable skills that you can develop is being able to sketch a TXY and PXY phase diagram, right? So that now I can use that to visualize or interpret what the data is that I'm given here, but then I'll be able to use that in terms of solving A. Okay. So in A, we're told we have a solution that contains 30% by mole methanol, and it's flashed to 1 bar, 70.82 degrees C. Determine the phase of the system. If two phases, report the composition and relative amounts of each. Okay. So this one bar, okay, where this comes in is this is TXY data. And so TXY data, pressure is fixed. And so we're told that the pressure is 1 bar. Okay, and so component 1, so what's given here is methanol. So what I want to think about is if I open up my TXY, okay, key is let's just call this line, let's just say this corresponds to composition of 0.3 mole fracs. Okay, so remember notation, Z1 is going to correspond to system mole fracs. Okay, so my system mole frac is 0.3. Now my reference point, right, or my reference points, if I have a system of 0.3 mole fracs and I draw this vertical line up, okay, my two key points are going to be T-bubs and T-dew. So the idea is if my temperature of my system is less than T-bubs, okay, then that means I'm down here, I'm a liquid. If my temperature is greater than T-dew, that means I'm up here, I'm a vapor. And if I'm between T-bubs and T-dew, that means I'm in here, I'm two-phase. And if I'm in the two-phase, then I could draw my isotherm across my phase diagram and determine the composition of the liquid and vapor in coexistence. Okay. So if I were to label this, so at 0.3 mole fracs, here's T-bubs and here's T-dew. So T-bubs is 73.19. Okay, so let me go ahead and label that. T-bubs is 73.19. Okay, and T-dew is 74.70. Okay, that's degrees C if I can squeeze it in. So the temperature of interest now, right? Okay, and again, T-dew is greater than T-bubs. If it wasn't, then I'm in trouble, right? And I can look at my picture and I could say, hey, T-dew must be greater than T-bubs. But now if I look at the problem, right, we're told that we have a system at 70.82 degrees C. So the question is, where is 70.82 degrees C on my phase diagram? Okay, so I have a system, right? So I'm going to be on this vertical line because this is going to correspond to a system of 0.3 mole fracs. And I'm at a temperature which is less than T-bubs, right? I'm at 70 point something degrees C. So what that tells us then is for A, okay, so for A, since T is less than T-bubs, we have a liquid. All right, you can say we'd have a liquid of composition Z1 is equal to 0.3. Okay. Cool. So in A, the key is I sketch my phase diagram. I have my vertical line here corresponding to the composition of my system. And key is having my reference point of T-bubs and T-dew. If my temperature is greater than T-dew, then I'm up here, I'm a vapor. If it's less than T-bubs, then I'm down here, I'm a liquid. So up here I'm a vapor, down here I'm a liquid. And if in between, I'm a two-phase. And if I was in between, then I would draw my isotherm across and read off the composition of my liquid and vapor. And let's see, we might be asked to do that in B. Okay. So now in B, it says, what is the maximum mole frac of methanol that could be achieved when a solution with 30% methanol is flashed to 1 bar? All right. So methanol is my most volatile component, right? Component 1 is methanol, component 2 is ethanol. So component 1 is methanol. I have a system here, okay, and I don't expect it to exhibit an azeotrope. I guess we'll see when we plot it, right? But I don't expect an azeotrope. So if I have a normal system, I expect to concentrate the most volatile component in the vapor phase. Okay? The most volatile component is in the vapor phase. That's why we plot our TXYs and PXYs with respect to the most volatile component, because the most volatile component is the species of interest that we're trying to concentrate in the vapor phase. And when I say concentrate, we're trying to create a vapor phase where Y1 is greater than Z1. Okay. So, all right, so in terms of methanol, it's my most volatile component. I'm going to concentrate methanol in the vapor phase, or it's in the vapor phase where I expect Y1 is going to be greater than Z1. Where I'm going to get the largest possible Y1 is going to be at the bubble point. And so if I wanted the largest possible Y, okay, so I'm going to keep my T-bub temperature on there. So let me draw a line trying to through it. So if I have a mixture of 0.3 mole fracs where I hit my bubble line, that corresponds to my bubble point. Okay, so I'm going to draw my isotherm across. Okay, and the significance of this is this y1 that I would read off is going to correspond to my largest possible y that I could achieve. Right, as the temperature increases, if I were to draw on another isotherm, right, the value of y1 is decreasing. The largest y I can achieve for this system is at the bubble point, right, and that's going to give me y1 max. Okay, the bubble point's interesting because x1 is equal to z1, and so I'm still going to have essentially all liquid. It's a limit. Okay, but what's key is y1 max is going to happen at my bubble point. Okay, is concept one. And then concept two is, well, now we've got to think about how the data that we have is presented. So I know if I have a mixture of 0.3 mole fracs, that is going to, bubble point temperature, if I read off, is going to where I'm going to get the largest possible y. Now the question is, well, what temperature, or what is y1? Well, how I'll get y1 from the data we're given is, remember, the data is tabulated as essentially, the data provided is essentially, I'm looking at vertical lines of a constant composition, and so for this line, right, I have T bubs and T dew, right? And so what I'm going to look for is, well, this is T bubs at 0.3 mole fracs. Okay, I'm going to look for when T dew is equal to 73.19 degrees C. Okay, so when I have 0.3 mole fracs, okay, T bubs is 73.19 degrees C. So at the bubble point, I draw my isotherm across, or I hit my dew line. That's going to correspond to y1 max. I want to know what y1 max is. Well, in the context of how the data is tabulated, I'm thinking of, this vertical line, and then we're given T dew and, or T bubs and T dew for that given composition. Okay, well, on this line here, I know T dew, and what I want to find is for that T dew what the corresponding composition is. Okay, and we'll go over to MATLAB, but just looking at the data to try and feel our way through it, is what I'm looking for is when T bubs, right, was 73.19. So I want to find where I get 73.19 in terms of T dew. And so that's going to come between 0.4 and 0.5 mole fracs. So I know it's going to be between 0.4 and 0.5 mole fracs. How we're going to get that is via interpolation. And so in 314, you probably memorize some interpolation equation. I'm just going to do it in MATLAB because it's easy. Okay. But again, key is just being able to pictorially represent what we have going on, so that when I have this data, I know how to actually use the data. Okay. All right, so what I have shared with you is in this MATLAB folder that I've shared with you all in Chapter 8, there's MATLAB files for Problem 1 data and Problem 2 data. So here's just the Problem 1 data up. And I'm just going to save it as like Problem 1 solution. Okay, that way you have the data still available there in case you want it. Okay, and so, yeah, let's do it. So the first column in the data we were given was x1 or y1, so I just created a separate vector for x1 and y1. Then I have T dew and T bubs. And so I'm going to call this y1, and this is for B. Oh yeah, I forgot. MATLAB had, my screen recorder has an issue with my equal sign. Shoot. Why, I don't know. So let me arc. So I'm going to do this without assigning the variable to anything. So ideally I would do something like y1b equals, so I can assign the result to it. But for some reason my screen recorder gets mad when I use MATLAB Online with my equal sign. It doesn't happen if I'm not using MATLAB Online, so I don't have an explanation for you, but let's do it. So this is going to be y1b. So I would do like y1b equals and interp1. So I'm going to interp1 is MATLAB's linear interpolation function. And so first argument is my um, essentially my y variable, my um, dependent variable, my independent variable, and then I should have to specify the value in which I want to interpolate at. Right? Pretty sure, right? It's been a right, and so if you can't remember, so if I do a doc interp1, right, it will tell me exactly that. Okay, so let me go back. Okay, so again, and actually when I put it up here, it's xy then x. Okay, so let's get it. So interp is going to be tdo y1, and then my tdo was it tbubs is 73.19. Okay, so if I save that and run it, okay, I get 0.4233. And so when I look at my data, oh, we said that it's going to be between 0.4 and 0.5, right? So it seems reasonable. Okay, and so jumping over to MATLAB, okay, remember this is essentially, in this case, my independent variable, my dependent variable, and then the value of my independent variable in which I want to estimate the value of my dependent variable. Okay, so xy, and then there's my x value I want to estimate it at. And so if I were to do this, all right, I would assign this to variable, but I blame my screen recorder, and that's that. Okay, cool. So I get 0.4233, and so that's B. If I want to find the maximum mole frac of ethanol, well, ethanol is the least volatile component. I'm going to concentrate it in the liquid phase. And so maximizing x2 is the same as minimizing x1. And so that's going to happen at my dew line. Okay, so that's going to be the furthest I'll be able to get to the left on my bubble line. And so then I would just be looking for, so if this were, x1 min, so I just need to find, so that's tbubs. Yeah, so that's tbubs. So now I just need to do the same interpolation. I'm thinking, I'm losing my mind here. So tdo 74.70. So I need to find when tbubs is 74.70. That'll give me x1, and 1 minus it is x2. Okay. So we'll compute it. We'll see if it looks reasonable. So now I'm going to interpolate in tbubs. Compute my x value of 1. tbubs is 73. Nope, not 73.19. When I get tbubs is equal to tdo 74.70. Okay, bam. So if I run this, I get a x1 min of 0.2013. Okay, and so 1 minus that would actually then correspond to my max, which is 0.7987. Okay, so I'm going to do both. So this is y1 max, that's x1 min, and then 1 minus it is x2 max. Okay, so let's see, is 0.2 reasonable? Well, if I look at my tabulated data, I'm looking for, so here's tdo. Okay, so now I'm looking for when tbubs is 74.70. It's going to happen right about 0.2 here. It's between 0.2 and 0.3, closer to 0.2. Right, so our value of 0.2013 seems reasonable for x1 min, and that's going to correspond to an x2 max of 0.7987. Okay, cool. Right, and ideally you would assign these to variables, but I'm having issues. Okay, cool. And then C, Let's make a plot, right? We can make a plot in MATLAB, and then in terms of annotating it, we can label it, but ideally you would have, say, a printout, and you would draw a bubble line, do line, and all of that good stuff on here. But let's plot it, and then we can say what it is. Okay, and so, okay, I'm going to do a hold on. Okay, and I'm going to plot t do versus y1, and I'm going to make that a red line. Then I'm going to plot t bubs versus x1, and we'll make that a black line. We'll have a x label that's going to be x1 or y1. Y label will be t in degree c. I think it's getting messed up because I didn't put it in quotes. Let's see if that works in terms of degree c. And then, yeah, you could always add a title or all of that fun stuff. But let's see. So if I run it, I get a figure. So here's my temperature in degree C. Oh, so let me see. Try and get my superscript to work. All right, so I get my temperature in degree C, then x1 or y1, all right, and cool. So down here is going to be liquid, up here is vapor. This is my dew line, that's my bubble line, two phase in between. Here's T2 sat, here's T1 sat, and I flip my axes. Ba-da-da-bum. Oh, not there. Y1, comma, T2, X1, comma, T-bubs. It's a good thing I am not taking 324 this semester. Yeah, so now X is going from 0 to 1, and there's T. All right, so liquid, vapor, two phase, dew line, bubble line, all right, two phase in between. Okay, and so yeah, that's all there is to it. Now let me actually do something. So this is going to be, so I'm going to call this figure 1. And so while I have your attention, RJ had asked a question of what if we switched the role of the most volatile component and least volatile component. Okay, and so what I'm going to do, so I'm going to copy this, but instead of y1, I'm going to plot as 1 minus y1, so that'd be component 2, and I'll plot 1 minus x1, which would correspond to component 2 as well. Yeah. So if I were to plot this, all right, figure 1 looks normal, right? Then figure 2 is the mirror image. Okay. So this is where component 1 is my most volatile component, right? That's what I'm plotting with respect to. And what's key is if I draw my isotherm across, right, my dew line's to the right of my bubble line, y is greater than x. If I plot with respect to the least volatile component, it switches, right? So here it's nice because I have color-coded things. So I notice T2 sats greater than T1 sat, but now I get T1 sats greater than T2 sat, so I'm plotting with respect to the least volatile component. I draw an isotherm across, and my bubble line's to the right of my dew line, so I get x1 is greater than y1. Right? And so there's the, what would happen if you had plotted with respect to the least volatile component, and you could perform the same analyses. It's just you need to be, careful and orient yourself with the graph. Okay, hope that helps. Again, I would have assigned these two variables, but I'm having an issue signed with an equal in a web page with my screen recorder. Didn't used to happen with MATLAB, but hopefully that helps. And this is also online in case you want some help to be able to do that. Okay, let me know if you have any questions.